There we go. So that is what we'll be talking about today, is natural frequency, interference, boundaries, and standing waves. You should write it down. It is my watch has the date on it? Some watches.
Where?
A little
Tiny little square next to the 3. It says 24. Did you write down the title? Do you not need the title? So you did write that. All right, everybody got it? Bam! All right, so first thing we got to talk about is what's called natural frequency. This is sometimes called fundamental frequency. They're technically not exactly the same thing, but they're so close that we're not going to worry about a distinction for the purposes of what we're doing this year. All right, so natural frequency, fundamental frequency. All right, so the idea is when you strike something or displace it in some way, the frequency that it vibrates at is called the natural or fundamental frequency. Write that down, and then I will show you a few examples. Hope you all already started. What?
What did I forget about that?
Oh, I won't forget. It's sticking awkwardly out of my pocket. All right, is everyone done writing?
Yes.
Okay, so natural frequency. So there's a bunch of examples of natural frequency. An obvious example is that if you pluck like a guitar string, right? The frequency that it vibrates at is determined by its natural frequency. When you tune it, you're changing the natural frequency, right? And thus changing the frequency that it vibrates at. Okay? Natural frequency is why when I drop stuff, you can tell what it is by the sound it makes. Okay, I'm going to drop some stuff. Tell me what it is. You ready? Here's item number 1.
A quarter.
Some sort of coin. Here's object number 2. Tell me what it is.
I can see it.
Well, don't look at me, cheater.
Where am I supposed to put that?
I don't know. Object number 3.
Marker.
Okay, but so anyway, you can, by the sounds they make, you can tell what they are, right? Okay? That's because when they hit the ground strikes them, causes them to vibrate, they make sound, you go, oh, a quarter, right? Okay? Similarly, when you push a kid on a swing, they swing back and forth, which weirdly is technically vibrating, right? Very slowly, but vibrating nonetheless. And there is sort of a natural frequency to a swing, okay? My daughter Sally just learned how to pump. She's super excited because she can now pump herself on the swings. The first time I was like, go on, pump, you know? She like just wiggled her legs back and forth super quick. And she's like, I'm not going anywhere, right? And it's because when you pump, you need to pump at a frequency that matches the swing's natural frequency, right? Like think about it. You pump your legs once per swing of the swing, right? Follow? Question? Okay, cool. So those are different examples of natural frequencies. All right. Other examples are, what did I do with it? I put here stick. Stick. So if I pluck this meter stick, it makes a sound. If I change the length of it, it makes a different sound. Right? So I'm just changing the natural frequency. Cool? All right. Questions? All right. That's natural frequency. All right. That was thing one. Thing two. Oh. Here we go. Interference. Interference is something that occurs when waves cross paths. Noise-canceling headphones work on the principle of interference. Auditoriums that have good acoustics try to prevent interference. Okay, so write down those two definitions, and I will explainify. Either one will work. Okay, cool. So, interference. Anytime two waves cross paths, they interfere, and there are two types of interference. So if you have two crests or two troughs meeting each other, it creates what's called constructive interference. The result is that you get an increase in amplitude, not an increase in wavelength, an increase in amplitude. All right? And then the other type of interference is called destructive interference. That occurs when you have a crest meeting a trough, and the result is a decrease in amplitude. All right? So, let me show you. All right, so, oh, darn it, I wanted to do boundaries before I did interference. Curse my feeble brain. All right, in a minute we're going to talk about boundaries, so let me just show you this real quick. So check it out. So I'm going to create a pulse that's going to go down here, and for some reason these are the real angular waves instead of, oh wait. I don't know. All right. Oh, because I have the amplitude set to 0. Sometimes I'm not very smart. Seriously? All right, there we go. Oh, no, we want to go bigger than that. There we go. Nope. Pulse width. Hold on, restart. Man, I had this all set up last hour and then... Well, that'll work. It's not ideal, but... There we go. Okay. Oh, it looks like I got the tension turned all the way down. That's what's wrong. Okay, so anyway, so wave pulse, right? So, in a minute we're going to talk about boundaries. This will all be written on the board in a second. But so a boundary is anytime a wave goes from one medium to another, we say that it encounters a boundary. All right? And when that happens, two things can happen. All right? One, some of the energy reflects. All right? So in this example, my medium is whatever, red beaded stuff, right? So right now, well, in a minute, the wave is going to be traveling through red beaded stuff, and then it's going to hit the metallic arm. That's a new medium, right? And so what happens is when the wave hits the new medium, some of the energy reflects back. Okay? At the other end, the wave is going from red beaded stuff to air. See how that end is open? So there's nothing to sort of absorb the energy. Okay, so the energy reflects. Okay? Some of it also gets transmitted into the new medium. We'll talk about that in a second. But so for right now, what you need to know is that the energy is going to basically reflect back and forth. Cool? Now, if I create another pulse, then I'll have two waves moving on this thing. They're going to be moving in opposite directions, and they're going to interfere with each other, right? So, in just a minute. All right, here we go. Boom. All right, so right now I have two waves that are traveling towards each other. I have one wave going this way, one wave going that way. They both have positive amplitudes, right? They're both crests, right? So they're going to move along and they're going to cross paths. And the resulting thing that we're going to see is what's called interference. All right, so I'm going to turn on the slow motion and let's watch what happens. Did I say that like a nature host? Watch, it's the squirrels. Here we go. Watch the amplitude. Bigger amplitude, right? Okay, so basically what happens there is the way that I always think of it is each of these waves sort of contains a positive amount of energy. It's a little sloppy, but you can kind of think of it that way. And when they cross paths, the two energies work together, resulting in a bigger amplitude. Follow? Okay, yep. Because they're both positive. Like what's a positive plus positive? A bigger positive, right? Sometimes they do cancel out though. So, in just a minute, instead of having a crest meeting a crest, we're going to have a crest meeting a trough. So now I've got a negative amplitude meeting a positive amplitude. So, what's a negative plus positive if the amplitude is the same? 0, right? Okay, so watch what happens. So for a split second, watch the amplitude. Get smaller, 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 boom. For a split second, they cancel each other out, right? I paused it a minute late, but does that make sense? Okay. Notice the waves are not bouncing off of each other. They're traveling through each other. Okay? And you can see that. You can't see it with the constructive interference. So here, we're going to get. So here's another example of constructive interference. These two guys are going to overlap. For a moment, our amplitude will spike. Negative plus a negative is a bigger negative. Notice, same wavelength, bigger amplitude. Okay, but, so notice, positive amplitude is going that way, negative amplitude is going that way. If they bounced off of each other, this one would go this way and then come back, right? If they don't bounce off of each other, what's going to happen is this crest here is going to disappear for a minute, but then it'll reappear still going this way. Okay, so watch. This one is moving to the right. It cancels out the negative one and it goes away, but then it reappears and it's still moving to the right just like it was before. Cool? So the waves literally go through each other, but for a moment their amplitudes add up. Cool? Any questions about interference? All right, so what do you need to know? Well, you need to be able to draw it. So let's draw this. All right, so the way I always drew this in my old school is I would say, all right, let's draw constructive interference. I'll draw it in blue since it's written in blue. So here's constructive interference. So if these two guys move towards each other, they're going to constructively interfere, resulting in a bigger amplitude and the same wavelength. So if this is an amplitude of A, and this is an amplitude of A, then this is an amplitude of 2A, right? A plus A. Cool. Now, Mr. McGuire has simplified things a scotch. And so what we're going to do is instead of drawing rounded wave pulses, we're going to draw squared off wave pulses. They're called Atari waves. That's like the technical name for them. So we're going to draw, whenever I give you an interference problem, on a homework assignment, our waves are going to be square. It's just how he draws them. It is what it is. He wrote the final, and it's the same idea. And I've given problems like this before too, so that's not me. I'm not trying to say one is better than the other. Just different ways of doing it. All right, so this guy is 2A. Well, what's Jonas? Yeah, I don't care which one you draw, as long as, this is what's on the plan. It's something squared. So, everybody good? Okay. And actually, there's one problem like that on the homework that was a problem that I wrote that's square. So, it's not this. All right. Destructive. So to make destructive interference, is destructive right up there, or was it green? Right? Okay. right? So this guy's going that way, that guy's going that way. What's going to happen when they cross paths? They cancel out, so you just get that, right? What if I give you this? Oh, I didn't give myself enough room. Hold on. We're going to fix that. Hold on, Anna. It's going to be okay. Oh, it's all okay. All right. So check it out. So this has an amplitude of, let's say, 1A. And this has an amplitude of, let's say, 3A. What's going to happen where they overlap, you guys? 2A, right? Because it's like -1 plus +3 equals +2. You could. Technically, yeah, you could do that. There's nothing wrong. Okay, so cool, you guys? That's interference. All right, if you in math class learn how to add graphs, that's all we're doing here. It's like this is a graph plus this graph, and you add them up, you get that graph. Cool. All righty. So that's interference. Let's see, what's next? Boundaries. Okay, so we talked about this before. This is not going to come up a ton. This is just one of those things. I feel like the word boundary comes up a lot. I don't know that you'll ever specifically have a question about it, but just when I talk about it, you need to know what it means. So a boundary just means that your wave is traveling from one medium to another. And when that happens, at least one of these two things will happen. Some of the energy will reflect and bounce back into the original medium, and some of it will refract and continue into the new medium. Write it down, and then I'll give you a couple simple examples. And then we can learn about standing waves and do some cool demos. Hooray! Oh, no. Embarrassing. Oh, pause. Thank you. Okay. All right. So we saw an example of this on the thing here, right? On this guy, right? Every time the wave goes from red beaded stuff to black arm thing, some of the energy reflects back. In addition, some of the energy gets transferred to this arm, and technically speaking, that arm would vibrate a little bit, right? When we were making waves on the Slinky before, I was disappointed at how strong Timor was, because when I sent the wave down the Slinky, his hand didn't move at all, right? But technically speaking, if he keeps his hand loose, a little bit of the energy gets transferred to his hand, right? Here's a simple example. Everybody look at the windows over there. All right, look around. If you look carefully, you can find a spot in the glass so you can tell that there's glass in the window. So what are you looking for to see if there's glass in the window? Smudge. Okay, smudge works. That's not what I was looking for, but a reflection, right? Okay, so when you look out the glass, you can see two things. One, you can see a little bit of a reflection, right? That's light going from air to glass and then bouncing back, reflecting, right? And you can also see the church across the parking lot. That's the light refracting. The light goes through the glass. Okay? Technically it's coming this way, but whatever, right? So that's an example of light changing mediums, and you've seen both the reflection, the light bouncing off of it, and what's on the other side of the glass is the light refracting through the glass. Cool? All right. Other examples of this. I was just talking about funny with Frank the other day. And they were up in the mountains with Yosemite Sam, and they kept causing avalanches by making noise. And so, Bugs Bunny would go, yoo-hoo, and then a moment later you'd hear, yoo-hoo, and then, right? So, yes, physics in Bugs Bunny. So when he shouts, yoo-hoo, and then a moment later he hears, yoo-hoo, what is that? Echo, which is sound reflecting, right? So the sound is traveling through the air until it hits the mountain, new medium, and then it bounces back, right? Okay, and then why does the avalanche start? Because the air particles vibrate the snow particles, so some of the energy goes into the snow instead of bouncing off of it. That shakes the snow and causes an avalanche, and Yosemite Sam gets tumbled back down to the bottom of the mountain. Cool? All right, you guys know who Yosemite Sam is? No, man, you guys gotta watch that. It's so good. Like, I'm not somebody who's like all about like the old days, but Bugs Bunny is really freaking funny. So check it out. Anyway, so are we good with reflection and refraction? Okay. Where was I? Okay, so that's that. That's that. All right. All right. Standing waves. I think this is the last part where you can write a whole bunch of definitions. There's some other stuff, but most of the other stuff is drawings. Ooh, I should pause the video. Thank you. I got you guys here to keep me on my toes. Okay, so standing waves. I think it's probably easiest to just show you. So here we go. All right, so right now, this little vise here represents this end being fixed. So this little green dot at the end of my medium is not going to move. And notice this is a fixed length, right? The length of this thing is not going to change, all right? So what I'm going to do is I'm going to create a wave in it by increasing my amplitude. Oh, arg. Try that again. I'm going to increase my amplitude. All right, so if you look at this, it's a wave. Not very exciting, right? Okay. It turns out, though, that there are certain frequencies for which we can create the illusion of the wave sort of standing in place. All right. The first such frequency for this particular setup happens to occur at 0.4 hertz. So give me one moment. 0.4 hertz. We will restart and watch. So basically looks like a jump rope, right? So there are 2 points here that are basically staying at rest. This point is more or less staying at rest. It's not perfect. And this point is staying at rest, right? When you pluck a guitar string or a violin string or whatever, this is what it's doing. The two ends are fixed, in the middle of it vibrates at its natural frequency. Okay? I'm sorry? Yes, yeah, you can see it, yeah, right, going around. All right, so that's a standing wave. All right, this is what's called the first harmonic. The natural frequency corresponds with the first harmonic. All right, and some of you have heard about harmonics. So the second harmonic occurs when you have double the natural frequency. Okay, double the fundamental frequency. All right, so if I double my frequency, we'll get another standing wave. All right. So let me increase my frequency. So right now it's 0.4, right? So double that would be 0.8. Let me just show you what happens. I'm going to increase it, but not all the way to 0.8. So let's increase it to that. So it's at 0.58 right now. So it no longer looks like it's staying in place, does it? Like, I mean, you can kind of see it kind of rippling back and forth, right? Okay. But if I get my frequency exactly right, make this amplitude a little smaller. All right. If you get the frequency exactly right, watch what happens. Watch this little green dot in the middle. It doesn't move, right? Basically. It's not perfect, but it's pretty close, right? All right, so this is what's called a standing wave. And it's called standing because would you say that this wave is moving to the right or moving to the left? Neither. It's a standing wave. All right? And the reason this happens is because what's happening is this thing is creating waves that go this way. What happens when the waves get to the boundary? They reflect back. What happens when waves going this way meet waves going this way? What's that called when two waves cross paths? They interfere, right? Okay, and there are different types of interference occurring at different points. This point right here is called a node. That is a point where, due to the frequencies of the waves, this is always destructive interference. So whatever wave is going this way is exactly canceled out by a wave going this way. Okay, it's called a node. We'll write this all down at some point the next day or two. These points over here are called antinodes. That's always where there's constructive interference, right? Because your amplitude is bigger. Now, sometimes the amplitude is 0 because you've got, you can have an amplitude of 0 plus 0 equals 0, okay? Which is why it gets smaller sometimes. So that's a standing wave. Good? So this is the second harmonic because I doubled my natural frequency. So my natural frequency was 0.4. Second harmonic's at 0.8. Where would the next one be? Close. 1.2. So it's multiples of your natural frequency. Right, so you don't necessarily have to double it every time, which is I think what you were thinking. So our natural frequency, our fundamental frequency is 0.4. So 0.4 times 2 is this. 0.4 times 3 is 1.2. All right, so before I do that, well, we'll do it since we brought it up. Computer. All right, so I just tripled my fundamental frequency, and it looks like that, right? Standing again, right? So our fundamental frequency looked like this, right? Often called the first harmonic. Yeah. The second one looked like this. That's the second harmonic. And then the third one looks like this, right? That's the third harmonic. So every harmonic adds, how long is, well, let's start with this. How long is this? There you go. Say it again.
One wave.
One wavelength, right? Isn't this one wavelength, you guys? Look. Right? Okay. How about this? Exactly. That's half of a wavelength, right? You're getting just one crest instead of crest and a trough, right? And over here we've got 1.5, right? Follow? All right. So that's what it looks like if both ends are fixed. Okay. Now, you don't always have this. Like air, like if you play a wind instrument, the ends of the tube are open, right? So the air is free to vibrate at the two ends. All right. So some instruments have one end closed off, some have neither end closed off. All right. This won't let me open both ends, but I can open one side. So let me do this real quick. I'm happy with this. It's not going as smoothly as I hoped it would. All right, so right now this is a fixed end, right? Because this little thing can't move. I'm going to change it to loose end. So now this end is free to move. All right, and everything kind of falls apart now, right? This doesn't look like a standing wave anymore, does it? Okay. So let's see. Before my natural frequency was at 0.4, and this isn't working. Let me try. I'm going to try 1. Restart it. Let's see what happens here. Oh, that looks like that's working. I've got a node right here and a node right here, right? Does that make sense? So where those two X's are my nodes. All right, so that gave me some sort of harmonic, but it's not the fundamental harmonic because I think I can go to a lower frequency and get this to work. All right, so Let's try lowering it by 0.4. That was what we did before. We increased it by 0.4. So let's try decreasing it by 0.4 and see what happens. So I'm going to go down to 0.6. There we go. Restart it. Let's see what this looks like. Oh, that's standing also. Here's my node. Follow? All right, well, let's try decreasing it again and see what that does. So if I decrease it by another 0.4, we're going to get down to 0.2. This one gives us the fundamental frequency for this one. Notice the fundamental frequency is different now because we don't have two closed ends anymore. We got one closed end and one open end. And so now what's happening is the wave looks like, so the first one I gave you looked like this. This one looks like, or the second one I gave you looked like this. And this one looks like this, right? Okay, so how many wavelengths is this, you guys? It's not even a half, right? A half would be this, but we've got a quarter of a wavelength, right? Okay, so this is the first harmonic because it's a quarter of a wavelength. How many quarters is this? 3 quarters, isn't it? Right? 1, 2, 3. So that's the third harmonic. And so this is the first harmonic. This one's the third harmonic. How about this? How many quarters is it? 1, 2, 3, 4. That's a whole wavelength, so that adds up. 5, so that's the fifth harmonic. Okay. And to double check, look, my fundamental frequency occurs at 0.2 hertz, right? And this was at 1, right? So what's 0.2 times 5? What's 20 cents times 5 again? $1, right? So 1. So if I multiply my frequency by 5, it gives me the fifth harmonic. All right. So this is weird, and we'll write this down either later this hour or probably on Monday, to be honest. It turns out if you have one open and one closed, you can only get odd-numbered harmonics. Okay. All right. And finally, you can also have both ends open, but this little thing here won't let me show you both ends open. So let me show you both ends open. All right, so before I do that, let me show you a couple examples of this. All right, again, your homework, do as much of 8.3, which is really supposed to be called 9.3, as you can. All right, so check it out. So I've got a tuning fork here. This tuning fork has a frequency of 329.6 hertz. It is an E note, if you care. Okay? So that has a frequency of 329. The speed of air determines its wavelength, right? Okay? I'm going to see if I can. Well, we're not going to actually do the calculation, but you could calculate that wavelength. You hear it get louder there? Okay, what I just did is I created a standing wave inside this tube. And it only works at the right length. Right? If it's too long, it doesn't work. If it's too short, it doesn't work. So the idea is, one end of this is open, the top end is open. There's water in here, so the bottom end is closed. So the length of this tube right now must be a quarter of a wavelength. Does that make sense? All right, now, open-ended. Let me just show you this one thing real quick, and then we'll have to talk more on Monday. Put yourself somewhere where you can see this little thing over here on the floor if you want. As well you should be. Look out, Will, there's fire! Okay, this is a tube which is opened at both ends. I wonder what happens if I set it on fire.
by it's like. Oh.
All right. This is a column that is open at both ends. Uh-oh. Guess I should watch what I'm doing.
Whole thing goes like the flames.
Okay, so what's happening there, you guys, is the fire is hot. What happens to hot air? Rises. The hot air rushes through the column, causes it to vibrate, and it gives us the fundamental harmonic for the length of that tube. Okay? All right, do the best you can with the homework. I know we haven't covered a lot of it, but at least try it so we can try to get that test in on Thursday, all right? We'll talk more Monday. Have a good weekend. Thank you.
That was fun.
I don't want to
Fire.
stand.
Fire.
I just want, Jeff. You don't need to do it. All different.
See you later.
No, we don't need to do it.
Mike Jones, what are we doing here? Oh no! I told you to come in 4th hour today, and I'm no longer getting that test. Alright.
It was fun. I have a lot of work anyway to make it this weekend.
Okay.
So, and I gave those two assignments to do the 8.4 and the 8.5 worksheet.
Gotcha. Okay.
So,
Okay. Sounds good. And that'll actually help with procrastinating. All right. Cool. Thank you for being flexible. I apologize. It was a last minute change yesterday. 4 hours like we're not ready for this test. And I said, okay, let's take it later. Because I'm nice. All right, have a good weekend then. I'll see you on Monday, and we'll work Tuesday, 4th hour.
alright,
If I forget, remind me. I may forget over the weekend.
alright.